In this video, we're going to look at tangent planes and linear approximations. We will also explain what it means to be differentiable in two or more variables, and then also look at the differential to approximate the change in a function when we have two or more variables. So let's start it with a warm-up. Let's look at the normal and tangent vectors for the given point. Now, I'm going to approach the first one by using implicit differentiation. So we're going to go ahead and differentiate, and I get 2x. And then we know that x and y are multiplied together, so I'm going to use the product rule. So it'll be the derivative of x and then multiplied by y, and the derivative of x is just 1. And then the derivative of y, so dy and dx, multiplied by x. And then plus the 2y dy dx, and this equals 0. So we're going to go ahead and solve for dy dx. So dy dx is going to be equal to, and I end up with negative 2x minus y divided by x plus 2y. Now what I'm going to do is I'm going to go ahead and evaluate my derivative here at the given points. I'm going to evaluate dy dx at x at the point, I'll do it this way. Do it at the point negative 1, negative 1. Now when I do that, I end up with negative 1. So that's the slope of my tangent. So I just need a vector that will satisfy a slope of a tangent of negative 1. Now dy dx, delta y delta x, is equal to negative 1, which means I can write this as negative 1 over 1. Or I can write this as 1 over negative 1. Doesn't really matter. What I need is a vector that will have that same direction. And one of the vectors that would have that same direction would be a vector that starts at 1 and then goes to negative 1 for the I being 1 and negative 1. This, if I were to draw this vector, would look something like this. I would go positive 1 and then down 1, and so that would be a possible vector. Another vector that I could use is I could use the vector of 1 and negative 1 and positive 1. So if I go negative 1 and positive 1, this also is a vector that satisfies that direction. So my vector that is going to be tangential can be either one of these two. Either one of these two will satisfy it. Now, if we satisfy it with the first one, I'm going to call this V1, actually I'll call it T1 for tangential. So if I say the tangential is this first one, then I need a vector that is going to have the negative reciprocal slope in terms of direction. So I know that two slopes are perpendicular if the slope of one multiplied by the slope of the other equals negative 1. And so if one of them has a slope of negative 1, the other one has to be a slope of 1. So a vector that would be normal, the normal vector, so the normal vector to this would need to have a slope that is a positive 1. So I could choose 1, 1. So that would have a slope of positive 1. So positive 1 in the I, positive 1 in the j. So that would be a positive 1. Similarly, I could have chose them both to be negative. So if I choose my T1 to be my first vector there, then my first normal would be that. Or I could actually say that it doesn't matter. It doesn't matter if it's T1 or T2, T1 or T2, because they have the same direction. So my other normal vector I could have chose, so my second normal vector could have been negative 1, negative 1. And this also would come down here, so negative 1, negative 1. So negative 1, negative 1 is going to be normal to this vector or this vector, just like the 1, 1 would be normal to this vector or this vector. So that was the first one. Let's take a look at the second question, in which we're now in 3 space. So it'll be a little bit more interesting. And what I'm going to do on this one is I see that I have z here, and I'm going to see if I can get this z all by itself. So if I divide both sides by e raised to the x squared minus y squared. On this side, let's move the 3 over as well. Let's do this. Let's do z, e to the x squared minus y squared is equal to 3. Let's divide both sides by e to the x squared minus y squared, e to the x squared minus y squared. And then I'm going to have z all by itself, and that allows me to treat it as in 2D. And then I will still, of course, use the other things, but I'll be able to use partial derivatives on this one. So I didn't need to use partial derivatives on the first one, on A, but I'm going to use partial derivatives on this one. Now the thing is that this is 1 over e raised to the x squared minus y squared is the same thing as e raised to the negative x squared minus y squared, which is the same thing as e raised to the y squared minus x squared. So this is going to be y squared minus x squared. So now I'm going to use my partial derivatives. I'm going to go ahead and do the partial derivatives. Let me just erase that. So I'm going to do the partial derivative with respect to x first. So dz dx is going to be equal to, and it is 3e to the y squared minus x squared, and then it's going to be minus 2x. And then that gives me my partial derivative with respect to x to be equal negative 6xe raised to the y squared minus x squared. I'm going to evaluate this now. So my partial derivative, and I keep wanting to use d. My partial derivative, I'm going to evaluate it at just the x and y part, so at 2, 2. And when I do that, I'm going to get negative 6 multiplied by 2, e to the 0. So this gives me negative 12. Now I'm going to do the same thing. I'm going to do the partial derivative, and what I mean by the same thing, I'm going to do the partial derivative with respect to y. So I'm going to do that in blue. So dz dy is equal to, and in this case, I will have, here, I need to erase that too. Give me a moment to erase that. All right, so going back over here, I am going to have 3e to the y squared minus x squared multiplied by now 2x. So this is going to be equal to 6xe to the y squared minus x squared. And of course, I'm going to do the partial derivative and evaluate it. And it's the y at 2, 2, which gives me now a positive 12. To find a normal vector to my surface of my function, at the point x naught, y naught, and my output being f of x naught, y naught, I need to get in a vector that's going to be parallel to the tangent of the curve that is going to be produced by the intersection of the planes y is equal to y naught and the surface of f at this point, right here. And I also need another vector that's going to be parallel to the curve produced by the intersection of x is equal to x naught and that point. Then from there, we can do the normal, which will be the first vector crossed with the second vector. So since the first tangent is the partial derivative with respect to x, and the second tangent is the partial derivative with respect to y, these are the slopes. So we know we can have v1 to be equal to 1, 0, and then that slope, which is 12. I think it was negative 12 for the first one. And then I can have the second one, which is v2, and that's going to be 1, 0, 1, and positive 12. Now my normal is going to be the cross product of this. So I have I j, and k. 1, 0, negative 12, 0, 1, and positive 12. This is always the determinant. And this is going to give me, for the first component, to be 0, and then minus becomes plus, so positive 12. And then my second one, my second component, when I do this multiplication, and don't forget that it's also going to be a negative because it's a second component. So it'll be a minus 12, and then my last component will be a positive 1. And so that is the vector, the normal vector. Now here's the thing. I have, just like in my previous one, I could have also a negative, so it could be negative 12, positive 12, and negative 1. So that also will give me a vector that's normal. Now once I've found my normal vector, then I want to find my tangential vector. And with my tangential vector, there's an infinite number of tangential vectors. What we know is the dot product has to equal 0. So I could choose, I'll choose a tangential vector. So I'll my t vector, I could choose it to be, 1, 0, and negative 12. Then all I'd have to do is to confirm that this dot product is equal to 0. So there were my tangential, excuse me, and my normal vectors. Now you're thinking, why are we in vectors? Well, because we're going to use kind of some of that when we start doing some definitions. So let me just move this up out of the way. Let me move that up out of the way. Okay. So we're looking at tangent planes because we're in 3 dimensions. In 1 dimensions, we had a tangent line or actually it's 2 dimensions, excuse me. In 2 dimensions, we had a tangent line. In 3 space, we're going to have tangent planes because we can get an infinite number of lines that can be tangent to a point in 3 space. So let P naught be the point we're looking at on the surface of whatever is that our equation describes. Let C be a curve passing through our point that we're interested in, lying entirely on the surface. So it has to be on the surface. If the tangent lines to the curves C and P naught lie in the same plane, then this is called the tangent plane to C at P naught. So this is what we're talking about. So we have this tangent plane that's going to go through this point. It's going to pass through this curve C, and here's our surface S. For the tangent plane to a surface to exist, we can say that it is sufficient for the function that defines the surface to be differentiable at that point. We're going to explain what differentiality is later, so just kind of hang out later in this video, I mean. So let's see what it means to have an equation of a tangent line. The equation of the tangent line to the curve that is represented by the intersection of S with a vertical trace given by x is equal to x naught would be z is equal to f of x naught plus the partial derivative with respect to y of x naught y naught, and then y minus y naught. And the equation of the tangent line represented by the intersection of S and the vertical trace of given by y is equal to y naught is z f of x naught y naught with plus the partial derivative with respect to x of x naught y naught, and then x minus x naught. Now the parallel vector in the tangent line is given as this. A parallel vector to the second tangent line is given as this. If we take the cross product, kind of like what we did up above, we're going to get this. We're going to get the partial derivative with respect to x of x naught y naught in the I direction, the partial derivative with respect to y in the x naught y naught in the j direction, and then minus k. And this vector is perpendicular to both of the lines that we had before, and therefore is perpendicular to the tangent plane. We can use this vector as the normal vector to the tangent plane along with a point for the equation of a line, which is the equation of the plane, which ends up getting us to this point. So we do all of this and we get this. This is the equation of the tangent line, or the tangent plane, excuse me. This is the equation of the tangent plane. So f of x naught y naught plus a partial derivative with respect to x evaluated x naught, y naught, and then x minus x naught, and then plus the partial derivative with respect to y of x naught, y naught, and then y minus y naught. Another equation I want to give to you is the tangent plane equation at a point. So the other one at, say, P is x naught, y naught, and z naught. This is going to be equal to the partial derivative of your function with respect to x, evaluated at x naught and y naught, and then it'd be x minus x naught. So it's slightly different than the one that's given to us. And then I have plus the partial derivative of y, evaluated at x naught, x naught and y naught, and then y minus y naught, and then minus z naught. So it's just slightly different than this equation we have here. And don't worry, I will give this to you for the test, so don't panic on that. Now, it doesn't seem like we have a lot going on, so let's just kind of walk through this. The first thing we're going to want to do is we want to solve for z. So that's just going to make it easier to do the partial derivatives. You don't have to, but this is easy to get lost, so let's just solve for z. So I have negative 7z is equal to 8x plus 3y and then minus 19. Dividing everything by a negative 7, I have negative 8/7 x, and then plus, minus 3/7 y, and then plus 19 over 7. Now I'm going to do my partial derivative, so dz dx, and this is just going to give me negative 8/7. So I don't need to evaluate it because I have nothing to evaluate it with. I don't have any x or y there to substitute in to evaluate, so that's as good as that's going to get. And in fact, I could say that is evaluated at the point 1 comma negative 1 because I have no x or y to put in there. Now I'm going to do my partial derivative with respect to y. This is going to be something similar. This is going to be negative 3 over 7, and in fact, I can say this is evaluated at 1 comma negative 1 because I don't have any x and y in there. Now using this equation, I have got this piece, I have this piece, and then I just have to put everything in. So my first piece, which is my partial derivative with respect to x, is going to be negative 8/7, and then x minus, and then my x naught happens to be 1, and then plus my partial derivative with respect to y, which is negative 3/7, and y plus, or y, and then I wrote x, so y plus 1, and then minus z, and then it's minus 2. This is equal to 0. Sorry, that should be equal to 0. And then, so all we're going to do is let's go ahead and multiply everything by negative 7 because we can. And so we have negative 8, so it becomes positive 8x minus 1, and then plus 3y plus 1, and then this becomes plus 7z minus 2 is equal to 0. Now let's write it the way that we're used to seeing, which is x, y, z on one side and all the constants on the other. So we have 8x plus 3y plus 7z is equal to 19. And there it is. I can also write this as 8x plus 3y plus 7z, 7z minus 19 is equal to 0. Either one works. Okay, now let's take a look at this one. We want to take and find the plane at the point 0, 0, 0. We already have z isolated, so now we'll just do the partial derivative. So I'll do the partial derivative with respect to x. And this is going to give me 1 over 10x squared plus 2y squared plus 1 multiplied by 20x. I'm going to evaluate this at the point, so I'm going to do the evaluation, so dz and dx evaluated at the point 0, 0. And of course, this is just going to give me, well, 0. Now I'm going to do the partial derivative with respect to y, which is going to give me 1 over my 10x squared plus 2y squared plus 1 multiplied by 4y. And when I do this partial derivative with respect to y, evaluated at 0, 0, then this also gives me 0. Now, if I put this into my equation, this time I'm going to use the first equation, which you're thinking, why didn't I do that before? So this equation, well, I kind of did, and I didn't. So this z is equal to this function of x naught, y naught. This is the z. That's the output of 2. So if you put in 1 and negative 2, or 1 and negative 1, 2 will come out. So this actually is this z naught. So this equation is this equation. It's just, I think, wrote a little bit easier. So we're going to use the equation there, and we have 0. That's my partial derivative with respect to x of x minus 0. And then plus 0, that's my partial derivative of y, partial derivative of y with respect to x of y minus 0. And then, of course, I can put in my 0. That's my output for when I put in 0, 0. This is equal to z. So I'm using the first equation, which is pretty much what I wrote for the second one. And so I end up with z is equal to 0. And that is my plane. So in other words, I have the xy plane is my tangential plane to that curve right there. Let's take a look at this one. Again, we're going to do the same thing. We're going to do our partial derivative. So I do my partial derivative of z with respect to x. And so I'm going to have the cosine of x, and then plus the cosine of x plus y. And the derivative of x is 1. So that's as good as that gets. So my partial derivative with respect to x evaluated at 0, 0 is going to give me the cosine of x, or cosine of 0, which is 1, and then the cosine of 0, which is 1, so that one is 2. Now I'm going to do my partial derivative with respect to y, and so this is going to be equal to the sine of y plus the sine of xy, I want to do that again. It's x plus y, and then the derivative of y, which is just 1. I'm now going to evaluate this at dz and dy, evaluated at 0, 0, and this is going to give me, oh, those are cosines. I don't know why I put signs there. Let me erase. Those are cosines. Derivative of sine is cosine all day long. Cosine. Okay, so cosine of 0 is, of course, 1, and then the cosine of 0, of course, is 1, so I end up with 2. Using the formula, which is z is equal to, I'm going to use again the first one, my output is z, that is this represents f of x naught, y naught, and then it's going to be plus my 2, x minus 0, and then plus my 2, y minus 0. And so I've got z is equal to 2x plus 2y, and I can leave it like that, or I can write it as 2x plus 2y minus z is equal to 0. I'll take either one of them. Okay, so while we're doing this, and we know that when we're in 2 dimensions, there are times in which we may have a continuous function, but it may not be differentiable. So in 3 space, that means that we have this continuous smooth, or we have this continuous curve surface, but the tangent plane may not exist. So here's an example in which the tangent plane does not exist. If I have x or y is equal to 0, then my function f of x is equal to 0. That's this case right here. So the value of the function does not change on either the x or y axis. So that means my partial derivative here with respect to x of x comma 0 would equal the same thing as the partial derivative of y of 0 comma y. And this will be 0 either way. So as either x or y approach 0, these partial derivatives will always be 0. However, if we approach the origin from a different direction, which we will explore later, but right now let's just say I'm going to explore it with our directional derivatives are going to happen in 4.6, so next quarter. So let's just explore a little bit now so we can kind of get a feel for it, kind of expose ourselves to it. So now let's suppose we go at the line y is equal to x. So if I have y is equal to x, then I'm looking at a function which is x comma x. Now I go back to my equation up there and I end up with x squared, and then I have the square root of 2x squared, which gives me x squared over x, the square root of 2, which is the absolute value of x, square root of 2. So when x is greater than 0 here, the slope of this curve is going to be equal to, so when I do the derivative, right, because this is one of the things where, remember, way back in calculus 1, and when we talked about the limit, and when we did the limit and we had this absolute value part, this part here, we had to approach from the negative and the positive. So we had to approach from the left side and the positive and the right side. Well, when we were approaching from the positive side of x, so when x is greater than 0, my slope, my derivative, my slope here is going to be equal to the square root of 2 over 2. However, when x is less than 0, my slope is going to be a negative number. So it's going to be negative square root of 2 over 2. Because these are not the same, that means that there's no way that this is going to have a tangent plane at that point. So even though it is continuous, there's no holes in it, we have a problem with the tangent plane because the way I approach it changes the way that the slopes are. So there is that. And we're going to do a lot more of that next quarter. And right now, it's just like, hey, just be aware, just because it's a continuous surface does not mean that it's differentiable everywhere. That's equivalent to when we had corners or vertical tangents into space. So now let's talk about linear approximations, because that is a natural progression when we're talking about differentiability. So in 2 dimensions, the linear approximation is given as this equation, that I can approximately doing f of x at x equals a, I can do it this. And if you remember in calculus 1, this is when we started talking about, well, hey, what if I wanted to do the square root of 15.99? And we said, hey, we can approximate it if we use a is equal to 16. And we said our function obviously is x raised to the 1/2. And we'd be able to approximate what 15.99 is without actually knowing what it is by using the linear approximation. We're going to do something similar to that here. So here's the linear approximation formula right here. And the idea behind using linear approximation is that if there's a point x naught, so let me just kind of move this down. If there's this point x naught, so we have this point x naught, y naught, at which we know the precise value at x, y is known, we know that, then we can get reasonably close to x naught, y naught with the linear approximation, i.e. the tangent line. And this will yield a value that is reasonably close to the exact value, and the plane that is used to find the linear approximation is also the tangent plane to the surface at that point x naught, y naught. So that's why we do it. Note, this equation also represents the tangent plane to the surface, defined by z is equal to xy at the point x naught, y naught. It's the same thing. It's kind of like we had before. So, find the linear approximation at the given point. Because this equation is similar to what we had before, we need to find the partial derivative. So dy or dz, df of x. And so this is just going to be, cosine is going to be considered a constant, so it'll be the cosine of y, e to the x, and then we do our partial derivative, so d of f dy, and now the e to the x is going to be considered a constant, so it's going to be negative e to the x sine of y. I want to go ahead and evaluate my partial derivative with respect to x at the point 0, 0. So we have the cosine of 0, which is 1, and times e to the 0, which gives me 1. The partial derivative with respect to x, y of 0, comma 0 is going to be 0 because the sine of 0 is 0 all day long. Now, my linear approximation, L of xy, is going to be equal to, it is my point that I start out with. So look, it's f of x naught, y naught. Now, I didn't have the x naught, y naught, so I better do f of 0, 0, because I didn't have that z. And I have the cosine of 0, e to the 0, well, that happens to be 1. So that's that part. And then I have my derivative with respect to x, which is 1, x minus 0. And then it's going to be my derivative with respect to y, which is 0, and then y minus 0. So I end up with this being x plus 1 or 1 plus x, and that's my final answer. Let's take a look at this one. Now, this one is a little bit different in the fact that I now have my x, y, and z here, which I didn't have before. So I'm going to have to do my partial derivative. So my partial derivative, df with respect to x, is going to be 1/2 x squared plus y squared plus z squared raised to the negative 1/2 and then multiplied by 2x. My partial derivative with respect to y, so dy, is going to be pretty much the same thing. To the negative 1/2 and 2y. Now this linear approximation is going to be slightly different because I'm going to take and expand this. So like I did before, L, x, and y and z. Still going to be still going to be this part, f of x naught, y naught, z naught. Now, then the partial with respect to x of x naught, y naught, and z naught, x minus x naught. And then I'm going to have plus my partial derivative with respect to y, evaluated at, they should be evaluated at x naught, y naught, and z naught, multiplied by y minus y naught. Let me get my notations here correct. Erase that. So notations should be evaluated at x naught, y naught, and z naught. And now we have the z, so f of z evaluated at x naught, y naught, and z naught. And then it's going to be z minus z naught. Okay, so that's because I'm going to do a linear approximation with x, y, and z. So coming back down here, which is what I needed, I also need here, I need to have my partial derivative with respect to z. So this is, of course, 1/2 x squared plus y squared plus z squared raised to the negative 1/2 and then 2z. Now I need to evaluate all of these. So I'm going to evaluate it at, so df of dx evaluated at 3, 2, and 6. Well, the thing is that this part will be the same for all of them, right? I'm going to have 3 squared, which is 9, plus 2 squared, which is 4, and then 6 squared, which is 36. So 36 plus 4 plus 9. That gives me 49, so that's nice. So we know that when we put in those numbers, right, in this part, This is going to be the square root of 49. And so for that part, this is going to be true in all of them. It's going to be 1 over 2 times the square root of 49. So in other words, 7. So that's going to be true for that one. It's going to be true for this one. I'm not done. So 1 over 2 and 7. And then it's going to be true for this one as well. df of dz evaluated at 3, 2, and 6. Okay, so this one also has a 2 multiplied by 3, and these 2's cancel. This has a 2 multiplied by 2, and those 2 cancel. And then this has a 2 multiplied by 6, and those 2 cancel. So now that we've found all of the evaluations, all we have to do now is put it in the right form. So my form is going to be first my output. So I have to figure out what my output is. My output, when I put in 3, 2, and 6 into my original function, my output is going to be 7. So my L of x, y, and z is going to be 7, and then it's going to be plus my slope in terms of the x, so my derivative with respect to x, which is going to be 3/7, and then x minus 3, and then plus 2/7, that's my derivative with respect to y, and y minus 2, and then plus the 6 over 7, and then my z minus 6. And then that is my final answer. And I'm just going to leave it like that. Now what we're asked to do is find the parametric equation for the normal line to the surface indicated at the point. Now recall from when we did equations of line in space, you need a point on the line and you need a vector that is parallel to the line. Then the equation of the line will be x minus x naught is equal to at. And usually what we do is we solve for, we did x is equal to x naught plus at, and y is equal to y naught plus bt, and then z is equal to z naught plus ct. So we're going to use that to find a parametric equation to the normal line to the surface, the indicated point. So we know that the vector that is going to be obtained from the normal will be the vector, which is going to be the partial derivative of z with respect to x, evaluated at x naught, y naught, and then we'll have the vector of z with respect to y of x naught, y naught, and -1. So what we're going to want to do is we're going to want to differentiate with respect to x using our implicit, because there's no way I can get z by itself. So I can't get z by itself, but I'm going to do it with respect to x. So I'm going to have 2x and then minus. Now what's going on here is the product rule where y is just a constant. So it'll be 8, the derivative of x, which is just x, is going to be 1, and so it'd be yz. And then minus 8, and it'll be x, y, dz, dx, partial derivative with respect to x. And that should be a partial, not a full d. The derivative of y squared is 0 because y is considered a constant at this moment. And then plus 12z, then dz, dx is equal to 0. So solving for dz, dx, I'm going to get negative 2x plus 8yz divided by 12z minus 8xy. Now I'm going to evaluate this at the point 1, 1, and 1. And so this is going to give me negative 2 plus 8 over 12 minus 8, which gives me 3/2. Now I'm going to do my derivative implicitly, derivative of z with respect to y. Now anywhere I see x, I'm going to treat it as a constant. So I'm jumping the gun there, it's just really excited. So I'm going to do the derivative of this with respect to y. And so I have negative 8xz. That's the derivative of y is 1. And then minus 8xy dz dy. And I have plus 2y, and then I have plus 12 dz dy, and that should have a z attached to it too. So let me erase that and put a z in there. So a z, and then dz dy is equal to 0. All right, now again, we're going to solve for dz dy. So I have 8xz minus 2y divided by negative 8xy plus 12z. I'm going to evaluate this with respect to the 1, 1, and 1. And when I put 1, 1, 1 into this, I'm going to get 8 minus 2 over negative 8 plus 12. Oh, I get 3/2 again. Well, that's kind of nice. Now, up here, we have this. Z, the derivative with respect to z of x naught, y naught, the derivative with respect to y, evaluated at x naught, y naught, and negative 1. If I then write these in terms of my point and my my parametric equation, then I'm going to end up with something that looks like this. I have x minus x naught is equal to my derivative, my partial derivative with respect to x naught, evaluated at x naught, y naught. Let me do it this way. Evaluated at x naught, y naught, multiplied by t. And then I'd have y minus y naught is equal to my partial derivative with respect to y, evaluated at x naught, y naught, t. And then, of course, I have my z minus z naught is equal to negative 1. Now, I then end up with, using my derivatives evaluated and my x naughts, I have y x minus 1 is equal to 3/2 t. Y minus 1 is equal to 3/2 t. And z minus 1 is equal to negative 1. And I think that should be negative t. That should be negative t. And that is my final answer, and this should be negative t. That's my final answer. If I want to, I could solve for x, so x equals, kind of like where I started out over here. As I said, hey, let's do x equals, so I could do it this way as well. Doesn't matter. So let's talk about what it means for it to be differentiable. Now, in 2D, the function is said to be differentiable at the point x is equal to a if f prime of x, or f prime, the derivative evaluated a, exists. Furthermore, it has to be a smooth, continuous, so the continuous is that x equals a, the derivative exists, which means it's, continuous, and it has to be a smooth curve, no corners, and the tangent line itself has to be well defined. That means no vertical tangents. In 3 dimensions, we need partial derivatives for this to exist at the point P, and the tangent plane to exist. To show smoothness, this is the most difficult to do. So let's give us some new vocabulary. The function fy is differentiable at the point p naught x naught if for all points x and y in a disk delta around p, we can write f of xy is equal to f of x naught y naught plus my partial derivative with respect to x, evaluated at x naught y naught, x minus x naught. And so this is the same formula we had before. The difference is that we've got this exy, and we call this the error term, and this e has to satisfy this. So this error term that we end up with has to satisfy this. There's a really good example in the book, and I looked through the book, the other examples in the book, the exercises, and I tried to find one that gave a really good example of this, and I couldn't find one. So I would recommend you look and read through the book, and we can discuss it in class tomorrow, but I couldn't find one as an exercise that we could go through. So we will talk about this more tomorrow if you'd like. Other important things that we get, other important theorems that we get are the differentiability implies continuity. So if it's differentiable, it's continuous. However, if it's continuous, it does not imply differentiability. We had that example earlier. And this last one is kind of important. It says, if the function and its partial derivatives are continuous at the point, then the function is differentiable. And you could check if the derivatives exist by using the definition of partial derivatives. So if the partial derivatives exist in that neighborhood that we're looking at and it's continuous, then the function is differentiable, which means obviously it's continuous. In 3 space, this is what it looks like in the 3 space. Notice this is the equation I gave earlier in different forms, but the same equation. I just didn't have this error here. So let's just do an example in which we're going to show that it's differentiable. Again, the one that I really wanted to do is already done in the book, so I didn't want to do the one that was already in the book because it's in the book, but I'll be happy to go through that in class tomorrow if you want. So let's go through this example, and the first thing we're going to do is we're going to use the theorem that the partial derivatives exist. So let's go ahead and do the partial derivatives. So I'm going to do df with respect to x first. No reason. I just like to do x first. No reason. And then this is going to be by the product rule. We're going to have 1 times e to the xy plus x e to the xy multiplied by y. Now, I'm going to do the same thing with my partial derivative with respect to y. And so this is going to be, well, e is just a constant, or x is just a constant now. So this is going to be x e to the xy multiplied by x. So I end up with x squared e to the xy. Now, we can see with either one of these derivatives. So let me do this one. Just kind of clean this up. This is equal to e to the xy plus xy e to the xy. We can see from looking at these partial derivatives that we can put any real number in for x or y, and what will come out is any real number. There's just no restrictions on the domain. So if there's no restrictions on the domain of these derivatives, that means they're going to exist everywhere in R2. And because this is going to exist everywhere in R2, then this is going to be differentiable at this point. So this one wasn't as interesting as the one in the book because we didn't have to explain what e, x, y, z is in a really nice example. But again, we'll look at that in the book if you want, because I just don't want to go over the same one that's already in the book, not here. Then we also get differentials. So if you remember in 2 space, we had something that looked like this. So the delta x is a differential, and the delta y is a differential. And in 3 space, it's going to look something similar. It's going to look like this. F of x, y, plus the derivative, partial derivative with respect to x of x naught, y naught, multiplied by its differential. And then f of partial derivative with respect to y evaluated x naught, y naught, and its differential. And here is graphically what we're doing. Here's the definition. Let z be a function in two variables with a domain f. Let delta x and delta y, these are the differentials, be chosen so that they are also in the domain of f. So I take my initial point plus this change in x, just a slight change in x. F is differentiable at the point x naught, y naught. So if it is, then the differentials dy dx are defined as this. And then the differential dz is called the total differential. And this is how we are going to define it. So let's take a look at some examples here. We want to find the total differential of the function z is equal to x plus y divided x times y divided by x plus y, where z or x changes from 10 to 10.5 and y changes from 10 to 15. So the first thing we're going to want to do is we're going to want to find the partial derivatives. So I'm going to find the partial derivative with respect to x. So dz dx is going to be equal to, well, I'm going to do unfortunately the quotient rule. So the derivative of the numerator, which is just y, multiplied by the denominator, which is x plus y, and then minus xy. Now remember, y is a constant, multiplied by the derivative of the denominator, which is just 1, and then x plus y, the quantity squared. I'm just going to clean this up just a little bit. So I'm going to get xy plus y squared minus xy over x squared plus y squared. Nope. No, it is not. X plus y, the quantity squared, which we see is going to give us some stuff kind of hanging out that likes this, so it just came along for the ride. It's going to give us y squared over x plus y, the quantity squared. Then what I'm going to do is I'm going to go ahead and find my partial derivative with respect to my y-axis, or my y variable. So dz and dy is equal to, and I'm going to do the same thing. It has to be the quotient rule. So it's going to be first x, and then x plus y, and then minus xy, and then 1, and then x plus y, the quantity squared. And this is going to give me something similar. When I multiply everything out, I'm going to get x squared over x plus y, the quantity squared. All right. So I've now got my partial derivative. So if I'm looking at what I've got here, as I've got these partial derivatives here and here. What I want to do now is to evaluate this at the given points. So I'm going to take my partial derivative with respect to x, and I'm going to evaluate it at the point, which is 10 and 15. So I'm going to evaluate it at 10 and 15. So this is going to be 15 squared over my 10 plus 15, the quantity squared. I'm also going to do my dz dy, evaluated at 10 and 15. And this is going to give me 10 squared over 10 plus 15 squared. Now my dz, and that's not a partial, is going to be equal to this value, which I'm going to get my calculator out, and I've got 15 squared, and then it's going to be divided by, hang with me, I'm just doing my calculator here, 25 squared. And so this is going to be equal to, when I'm looking at my partial derivative with the evaluation, that's going to be 0.36. So this is 0.36. Now, this is then the difference between them. So 10 to 15, I'm going to take I'm going from 10 to 10.5. This is my dx. This one I'm going to do the same thing. So I'm going to get 100 divided by 25 squared, and I get 0.16. So then this is going to be plus 0.16. That is my partial derivative evaluated at x naught, y naught. And then this goes from 15 to 13. So it ended at 13, but I started at 15. So when I get done, this is going to be approximately equal to 0.14, and it's going to be a negative. So that is my differential. And what I did is I broke it down into smaller pieces. I did first this, and then I did this, and then I evaluated it, and then I just said, okay, if I'm going from to, so it's always, I don't know why I did that. It's always going to be the differential, the dx and the dy. It's always going to be the 2 where I'm going to minus the from. So I went to 10.5 from 10, and I went to 11 from 15. All right, so now let's do actual applications. So there's real life applications for this. The volume of a right circular cylinder is given by this equation here. Find the differential, dv. So the first thing we're going to do is we're going to do the partial derivative with respect to x, or excuse me, r. So my dv is going to be my partial derivative with respect to r is going to be 2r pi multiplied by h. And then because we're doing the partial derivative, then it's going to be the delta r or dr. The partial derivative with respect to h then is going to be pi r squared and then dh. So that is the partial derivative and multiplied by my dh. So that is my differential right there. Now if I look at this part right here, that's the area, and we're looking at a right circular cylinder, that's the area of a circle. Can't spell area today. Let's try this again. That's the area of a circle. Now we're looking at a cylinder, right? So that could be the area of the base, or it could be the area of the top. So it's the area of a circle. And then if we take a look at this part, this is the surface area of the cylinder, not including the base. So that's a lateral surface area. Area. So that's what it means. My differential is there. Now, if I want to approximate the volume, estimate the volume of aluminum that's enclosed in the aluminum can with a diameter of 0.8 centimeters and a height of 12 centimeters if the aluminum is 0.4 centimeters thick. So then my dV is going to be equal to 2 pi, my r is 4, my h is 12, and then my dr is 0.04. And the reason my r is 4 is because I have a diameter of 8. And then I'm going to add to it plus pi. My r is here 4, the area of the circle. So the r is 4 squared. And then my dH is going to be 0.08. And the reason it's going to be 0.08 is because we have the thickness of the bottom and the top of the can. So we have this thickness, which is 0.04, and we have this thickness, which is also 0.04. So that's why that's 0.08. And so I'm going to get my calculator out, and this is going to be approximately equal to 16.084 centimeters cubed. And so that's about how much aluminum I need to make one aluminum can. Okay. The centripetal acceleration of a particle moving in a circle is given by this equation, where v is the velocity and r is the radius of the circle. Approximate the maximum percent error in measuring the acceleration using the errors of 13% in v and 2% in r. Recall the percentage error is the ratio of the amount of error over the original amount. So in this case, the percentage of error A is given by dA over A. So the first thing we're going to do is we're going to find our dA, or our differential. And we're going to do it by doing it first with respect to our derivative, and it's going to be with respect to r first. I guess we could do it with respect to v first. Let's do it with respect to v first. So it's going to be 2v and then r, because r is just a constant, and then it's going to be dv, and then it's going to be the derivative of r, which is r raised to the negative 1, so negative v squared over r squared, and then dr. Now, I'm going to say that a is equal to v squared over r. If I divide this by a, divide this by a, and then divide this by a, I've got dA over a, which is equal to 2VR. And then since I'm dividing by r, I'm multiplying by the reciprocal, which is r over v squared, dv, minus v squared over r squared, multiplied by the reciprocal, r over v squared, dr. So I end up with a dA over a is going to be equal to, these cancel, that gives me just v, so 2 over v dv minus, and that gives me an r, those cancel, that gives me that, minus 1 over r dr. So the fact that, and this is why I did this. You're like, why is she doing this now? Well, because what we have is the percentage of error A is given by dA over A. That's why I divide everything by A, because I needed a dA over A. Well, once I've got that, then I know that my dV over V has to equal the 2%. And then, of course, my dr over r has to equal that 3%. So the thing is, though, is that we have an absolute. So we're going to be looking at this as the absolute here and here. And I'm going to write it like this. And so my dA over A, this is my absolute, and this can be my max, is going to be 2 times 2% plus my 3%, and then absolute value. And so I end up with this approximately equaling to for about 7%, about 7%, about 7%. And that's it.